¿Qué tal? Buenas noches, soy Francisco Javier Szymanski Ángeles y voy a explicar los conceptos del capítulo 5 del libro de Física para Ingeniería y Ciencias de Bauer y Westphal. Y comenzamos con... en inglés. Bueno, ya. And we start with energy and how it affects our lives. I was thinking to do this with a little ball I had, but I lost it. So the first thing we have to see if we want to understand energy and its importance in physics, it's that energy is all around us, and the and what humanity's one of biggest problems is right now is that we are trying to find a way to use the most efficiently and the most not contaminable to the planet, because what we were doing up until the late 20th century was to use oil and carbon with a combustion reaction to power the things that we used, like trains, like factories, and that has come all the way to where we are now, and where we see our world getting deteriorated. So maybe I'm saying that energy is all around me, but let me explain. Energy has to do with everything we do on our daily lives. If energy wasn't here, I wouldn't be able to present to this presentation to you, or I wouldn't be able to play Smash on my GameCube, or I wouldn't be able to use my phone to record this, because it's all energy stored in the case of the phone, and energy through a whole lot and very complicated way to transport electric energy to my TV. And energy comes from the sun. We can find energy when the wind currents are very strong, when the sea level rises and it creates waves. It's all energy, and energy is all around us. It's like the force. Damn, that it's like the force. Well, I'm getting off topic. So now that we know, and nuclear is also a way that we have tried to get our energy from. But let's start with the concepts. First of all, we need to understand what was in the book was kinetic energy, but the best way to understand kinetic energy is to see kinetic and potential energy. So I'm going to use this ruler. I don't know if you see it, but I'm gonna use it. I'm gonna use this ruler to explain kinetic and potential energy. The best way to understand it is that in Spanish, potential is potencial, o sea que tiene. We can say that something has potencial, so that it can go further, or that it has the potential to do something. So in this case, the ruler, if I let it go, it has the potential to fall into the floor, and that's potential energy stored in the ruler. And this is a force that the earth applies called gravity, but this is the best way to understand potential energy. If I hold here the ruler, the time that I drop it, it's gonna fall, and all of the potential energy that it had stored from this point to this point is going to transform to kinetic energy, and it will be, for example, in this point it will have its max potential energy and zero kinetic energy. In this point it will have half of them, and right here, right before it goes to you into my hand, it has the lowest potential energy and the biggest kinetic energy. And one thing that we need to know is that kinetic energy can be is like distributed when a ruler or when an object is hits another object. In the example, this ruler, I'm going to drop it and I'm going to hold it with this hand. Well, I dropped it, but the thing is that now you heard how it fell on the floor, and that was the kinetic energy going to the floor, hitting it, and making the sound. Let's go to the next. Work. Work is the kinetic energy that, in this example, we'll keep the ruler, is the kinetic energy that that it's applied with another force. For example, is the ruler, in this case, the kinetic energy is being applied by the gravity from the earth, and what we know that the work that it takes from the ruler to get here to here, it's essential to know the force that it's being applied to the object. Or for example, if I use this box of game, I know that the kinetic energy that it has, that if I apply it pushing this way, it's going to, or just like going like this, it's the work that it takes that for the box to hit an object. And yeah, let's move to the next. Now let's talk to the work done by a variable force. In the example that I'm doing, like I'm pushing the box, it's not a constant, because it is accelerating, and my arm has a lot of things that makes it so that it's not a constant. So if we have the constant, if we have it constant, it's very easy to find it and to calculate the problems with constant with a constant force. But that's not the case in real life. So what we want is to know the work done by a variable force, in this example my arm. So for this we use this equation that has an integral, and an integral is, by the mathematic definition, it's the area inside a line or a parabola or something. So if we do a table with the force being on the y-axis and the time being on the x-axis, we're going to have a very weird and strange rect if it's a variable force. So what we want to know is what's behind it, and that's what this formula is for. Now let's move to a very, very interesting topic. It's spring force. And do I have a spring? No. But it's a very, not complicated, but it's very interesting. Let's say that you buy a spring from the market, you know, the ones with little collars, and the kids have it and they break it easily, but it's a nice 2 hours of fun. So let's say that I have it, that it's normal way, if I si las tiro y no, and it doesn't and it doesn't apply any force, and it's mm, in its natural state, let's say, it's going to have zero energy or zero forces, and it's a very different case from when I was pushing this box, because the energy and the force was always that way. And in the case of the spring from the mercado, if I hold it like this and I push it like this and I force it to be compressed, it's going to have a force directly outwards, so that it will push my hands, so that it will go to its natural position, and it being released. And if I push my hands like this and I si lo estiro, it's going to it's going to apply a force that it's going inwards, so that it will return to its natural state. And you know the classical, that like when you have una liga and you stretch it, and it's going to want to return to its natural state, and if you stretch it like this and one of your hands uh, let go of it, it's going to push on your other hand because of the forces that's going inwards. It's a very interesting thing. And now let's talk about power. We have talked about work, but what we want to know now is the work, but in a sense that we can measure it by the time that it was being applied to. For example, let's use the box again. So if I do this, the work, if we just want to work, we will get a value in joules. But if we want to know how much work is going through this phase, and then through this phase, and then through this phase, we're going to need power. That's why power is watt um, divided by time. So it's joules divided in seconds, which is the measurement called a watt. So that if we have 1 watt, it will be 1 joule applied in 1 second of the box. It won't be this fast, but it will be really really slow. So I think that's it. I'm gonna pause it. Well, turns out it wasn't it. So let's do a little recap of what we have seen in the chapter 5 of the Bauer and the other guy, physics para ingeniería y ciencias. Energy is everywhere. That's what we know, and humans are finding the most efficient and most reliable way to use the energy that's all around us. Because, for example, they all have their downsides. For example, solar energy and the panels, they are reliable of the sun. I mean, it's obvious, but in the night, the solar panels should store as much energy in the day, so that in the night it will still remain having energy. The wind turbines are very loud for the surrounding areas, even if they need really windy zones. They can be a problem for the citizens surrounding it. And nuclear it has a stigma since Chernobyl. I think that's it. Yeah, I think that's it. That something might go wrong and it could go, and it could be detrimental for everyone, even the world, because the radiation from the components of a nuclear plant are very detrimental to humans and their descendants, and they have a lot to do. So kinetic and potential energy. In the case of this skateboard man, one thing later. In the case of this skateboard man, we know that if he stands right here in the edge, and he drops to the little ramp, in the moment he drops, his potential energy is going to be the max, and his kinetic energy is going to be the least, even zero. And in this position that he is in, his potential energy is decreasing and his kinetic energy is increasing. And something that I forgot to mention last time is that something very important with the kinetic energy is the mass, because I don't know, this guy, I think he weighs maybe 50 kilos, 60 kilos, and if he goes in this ramp, he's going to have a set kinetic energy. But because kinetic energy is direct to the mass, if I do skateboard and I weigh 91 kilos, I'm going to have a bigger kinetic energy even if I have exactly the same procedure. I mean, the skateboard, and I go like this. So math is a very important thing. Work, I think we covered it, but work is the transformation of kinetic energy to, and the work it takes for it to move when a kinetic energy is being used by another force. It could be gravity, it could be an applied force, it could be the normal, it could be any force. And work done by a variable force. We just talked about this. It was the little kind of like graph. If we do the newtons, I mean the energy in here and the time in here, we could get a really weird. Let's search for one just for your entertainment. Time and newtons graph. Yeah, let's see this one. For example, here we would do let's say these are the newtons, and this is the time it transcurs. Let's say it's not like this, but let's say. So if we get this line, what this formula indicates us will be the area beneath here, so that we could know the work that is being done by the object that we're moving. And the spring force, its regular state, if we stretch it, it's going to have its forces going inwards so that it will return to its regular state. And if we compress it, its forces are going to go outward so that it can go to its regular state. And power is the work measured in time, how much work is going in a certain amount of time, so that if we want to calculate, this is power and this is work divided in time, that is joules divided in seconds, and it becomes watts. And now that's it. Thank you for watching and have a good one.